prove is that root 3 is irrational. Okay, so this is basically about a discrete math problem, and we will use another fact to prove this statement. So let's state the fact we are going to use. So if we say that not if, we will say that 3 divides n squared if and only if 3 divides n for n belongs to the set of integers. So the question here is, let's first of all explain the statement that 3 divides a square of an integer only if and only if 3 divides that integer itself. So what does it mean? So for example, if we take a number which is a perfect square, let's say 81. Now 3 divides 81 and the square root of 81 is 9. So 3 divides 9 as well. Okay, so this is one verification of this statement. I mean, we'll prove it later, but this is one verification. Now let's say 36. And then the square root of 36 is 6. So 3 divides both of them. Okay, now let's take a number 25. And the square root of that is 5. So 3 divides none of them. So this is also right. Okay, and then let's take a number. Now let's change the statement from 3 to any other number. Now I'd say 4. Let's write the same statements for 4. Now I'm going to say 4 divides. This bar represents divide. N squared, and if means if and only if. If 4 divides n. Is this statement correct? Let's see. Let's see, 16. Square root of 16 is 4. This is correct. Then we have 36. And square root of 36 is 6. Now 4 divides 36, but 4 does not divide 6. Okay, so this statement is wrong. So the above statement cannot be said about 4. Okay, now we have seen some examples and we have a pretty good idea that that statement is correct. But now let's formally prove that statement. So we say P is the statement that 3 divides n squared, and Q is the statement that 3 divides n. Okay, so what we are going to do is we are going to prove that if P then Q, and we are going to prove if Q then P. Okay, now I'm going to prove this one first. Okay, so Q is what? Q is that 3 divides n. If 3 divides n, then I can write n is equal to 3 times some integer m. Okay, and then I can write n squared is equal to 3 squared times m squared, which means that 3 times 3m squared. Now this means that in the factorization of n squared there is a 3 there. So this means that 3 does divide n squared. And how can I go from this step to this step? Think of it like this. If there is any number, let's say 1001. Now this number you can write it as 11 times some number. Now whatever this number is, we don't care, and if we see 111 here, then we can safely say that 11 divides 1001. Okay, so if we have only one factor of 3 in the whole factorization of n squared, we can easily conclude that 3 divides n squared. Okay, now we have proved that Q implies P, which means that if Q then P. Now we have to prove P implies Q. Okay, Now this is not very easy to prove. So what we are going to do is we are going to prove the contrapositive of that. So we are going to say not Q implies not P. Okay. So this is what we are going to prove. This and this, by the way, are same. Okay. So then I'm going to say that 3 does not divide n, which means that n can be 3m plus 1 or 3m plus 2. Okay, why only plus 1 and plus 2? Because if I say plus 3, then it divides it, because if I write 3m plus 3, then I can say 3 times m plus 1. Okay, so in other words, if any integer is divided by 3, the remainder is either 0, 1 or 2. Therefore I have a plus 1 or plus 2 here. Now let's take this case. Then I can say n squared, this is equal to 9m squared plus 6m plus 1. Then I can say 3 out here, 3m squared plus 2m plus 1. Now I can see that there is a remainder of 1 here, 1 here. Okay, so then I can say that 3 does not divide n squared here. Now let's go here. Now I have n squared is equal to 9m squared plus 2 times 2 times 3 is 12m plus 4, which I can write it as 9m squared plus 12m plus 3 plus 1, which I can write it as 3 times, actually this term does not matter one bit, plus 1 and then plus 1. The only thing which matters is this remainder. So then if we have a factorization of n squared, we can take 3 out, but there is a remainder of 1. This means that 3 does not divide n squared. So 3 does not divide n squared in this case and does not divide n squared in this case. So we can conclude that 3 does not divide n squared is in any case if 3 does not divide n. So what we have proved is not Q implies not P. Okay, so then again I'm going to rewrite it, that what we have proved is that 3, if 3 divides n, if and only if 3 divides n squared. Okay, now we are going to use this fact to prove that root 3 is irrational. Okay, now let's prove it by contradiction. So let's assume that we should say let here. So let root 3 be rational. So what is the definition of rational? A rational number, that number can be written as a fraction. So root 3 is equal to a over b, where a and b are some integers. Okay, so then we can say, we can square both sides and we can get a3 is equal to a squared over b squared, and then I can say 3b squared is equal to a squared. Okay, now this statement means that in a factorization of a squared I have a 3 somewhere. So this I can say that 3 divides a squared. Okay, now what? Now I can use this statement again. I can say I can write it again, 3b squared is equal to a squared, and I can bring let me write one more step. So a times a, then I can bring 3b squared over a, this is equal to a, and then I can say 3 times b over a and a, this is equal to a. Sorry, not a, b. Okay, now we have already assumed that a over b is a fraction. If a over b is a fraction, then b over a is also a fraction. So this means that if we put 3 outside, 3 in the factorization of a, we get a fraction somewhere. So this means that 3 does not divide a. Okay, now we have already seen that if 3 divides a squared, it has to divide a in all cases. Okay, but this is disproved here. So the only conclusion in this case is what? That our assumption was incorrect. So in this case we conclude that root 3 is not rational or irrational. Okay, so this is how we go through, you know, a typical proof. Now note that root 3 is irrational is, I mean, if you just plug it into the calculator, you will get a number which you can just see that it is irrational. But these techniques are really important to work with the basic set of integers, set of rational numbers, and basic premise of if and only if. We have to prove it both ways and use a fact to prove something which is obvious, but to prove it in a mathematical way. um, this is a very basic technique, you know, needed in discrete math. Okay, so this is about it for this video and hope you like it.